In this video, we're going to learn about antiderivatives. From our work with derivatives, we know that if the derivative f prime of x is equal to 2x, we can kind of work backwards and figure out what f of x was, because when we take the derivative, we know we use our power rule. So f of x in this case would have been x squared, right? And I can check that as f prime of x, and I use my power rule, it would be 2 to the x. Well, it might have had something else here. Maybe it was x squared plus 7, and I would still get 2x. Maybe it was x squared plus 8, and I would get 2x. Maybe it was x squared plus 8 pi, and I would still get 2x. Similarly, if I know that the derivative is equal to cosine of x, I can think backwards to figure out what f of x was. So the derivative of sine, again, is equal to cosine, so f prime of x would equal cosine x. But just like in that last example, maybe it was sine of x plus 7. That would give me the same derivative. Or sine of x plus 8, same derivative. Or sine of x plus 8 pi, same derivative. So here at the end, notice each time I'm just talking about a constant term. So when we deal with undoing a function to get its antiderivative, we have a few options. So the antiderivative is just giving us the function before we differentiated it. It's saying what was it to begin with. So we're kind of working backwards, but our notation can be just a little bit confusing. We use a capital letter F to denote an antiderivative of the regular function lowercase f of x. So that means that f prime of x, taking the derivative of the antiderivative, we would get the original function f of x. When we take the antiderivative, remember we kept adding a constant term. We're going to call that plus c. So the antiderivative plus a constant is the antiderivative of the original function. I can also say, so this is that symbol to tell us we're doing an antiderivative of the derivative of the antiderivative is equal to f of x plus c. So it gets a little bit confusing, but in general, the capital letter F is the antiderivative of what we took the derivative of. All right, let's try a couple. So I want to evaluate the antiderivative of 3 dx. So this sign here is also called an integral sign, and I know this was my derivative. So the f prime of x when I did this was 3, and I want to know what was the original function that I started with. So this tells me that the original function f of x is 3x plus some constant. I don't know what it was, but it's going to be a constant term because the derivative of a constant is equal to 0. All right, let's try another one. We want the integral of 11x to the 10th dx. So this tells me that my derivative was 11x to the 10th. So the original function that I started with had to have been x to the 11th plus some constant, which we don't know what it is yet. Now in this one we have to do a little bit of work first. We have 3x plus 1 times 4 minus x. So first thing I'm going to do is multiply this out. So I get 12x minus 3x squared plus 4 minus x. This is what my derivative was. I'm going to clean that up just a little bit more and put it in order. So this is negative 3x squared plus 11x plus 4 dx. So when I took my derivative, this is what I had, so I needed to work backwards. Well, if it was x squared and I'm working backwards, I know it had to start with a third, and then when I took my derivative, I multiplied. So this must be negative 1x to the third, because when I take that derivative, 3 times negative 1 would give me the negative 3, and then the x to the second, plus 11x. Well, if it's an x in the derivative, I know I started as x squared. So I multiplied something by 2 to get 11. So this is 11 over 2. And then plus 4x. And again, I have to remember there's some other constant. I don't know what it was. And this is getting my antiderivative. So again, using our rules in reverse. So since we had rules for derivatives, we also have rules for antiderivatives. So the opposite of our power rule says I'm going to add 1 to the exponent and then divide by whatever that exponent was. If I have a constant times a function, I can pull the constant out and then take the antiderivative of the function. And if I'm doing an antiderivative of a sum of functions, I can break it apart to the sum of each individual function. Okay, but a lot of times we want to be more specific. We want to know what was the specific function we started with. And in order to do that, we're going to need to know something else about the antiderivative, such as a point that satisfies the antiderivative. So for this problem, we want to find capital F of x, the antiderivative, given that f of x is 8x to the third minus 2x to the negative second, and f of 1 equals 5. So remember, this is that weird notation. They're telling me that f of x is already the derivative. So I'm just going to rewrite that. So this is 8x to the third minus 2x to the negative second. So to get my antiderivative, I'm doing the opposite of my power rule. So the exponent's going to increase by 1, and then I have to divide by that exponent. So this is minus 2 because that's a constant. Negative 2 has to increase by 1, so that becomes a negative 1, and I'm dividing by negative 1. So cleaning that up, I have that the antiderivative f of x is 2x to the fourth plus 2x to the negative first. And I can double check if I take that derivative that I'll get back to f of x. But now remember, there's also a constant here. We don't know what it is just yet. But now that we know what f of 1 is, we can evaluate f of 1 and solve for our c value. So we know f of 1 would equal 2 times 1 to the fourth plus 2 times 1 to the negative first plus c, and that value needs to work out to be 5. So here I have 2 plus c equals 5. I kind of ran out of room. I'm going to squeeze it up here at the top. So 2 plus c has to equal 5. So I know that c has to equal 1. So my specific antiderivative for this problem is equal to 2x to the fourth plus 2x to the negative first plus 1. Now for many antiderivatives, doing our integration, you will need to know some of the formulas. So there's a formula in our text, and then here again is a table of these formulas to help with our antiderivatives.